The alert that woke me up did not say disk full. It said something much stranger. API error rate spike. At 2:18 a.m., pager duty triggered. The on-call dashboard showed a sudden jump in HTTP 500 responses across multiple services. At first, it looked like a normal application issue. Error rate had climbed from under 1% to almost 30% in less than 2 minutes. Slack messages were already appearing. Is login failing for anyone else? Payment API returning 500s. Uploads are timing out. Grafana dashboards showed request latency climbing rapidly while error rates continued increasing. CPU looked normal. Memory looked normal. Network traffic was steady. From the metrics alone, nothing obvious was broken. But the application was clearly failing. Environment context. Our platform ran primarily on AWS. Application services were deployed in a Kubernetes cluster running on EKS. Around 140 pods handled API traffic, authentication, billing, and file uploads. Traffic averaged 3,000 to 5,000 requests per second. Persistent storage for several services used Kubernetes persistent volumes backed by AWS EBS volumes. One service in particular handled document uploads and file processing. That service stored temporary files on a mounted persistent volume. The backend database ran on PostgreSQL in Amazon RDS with automated backups and multi-availability zone replication. CI pipelines ran through GitHub Actions, which built container images and deployed them through Helm charts. Monitoring consisted of Prometheus for cluster metrics, Grafana dashboards for visualization, and Datadog alerts for application-level signals. Disk usage metrics existed, but most alerts focused on CPU, memory, and request latency. Initial symptoms. Users experienced the problem almost immediately. Login requests sometimes failed. File uploads stopped working completely. Some API calls returned generic internal server errors. Others hung for several seconds before timing out. At the same time, Kubernetes itself looked stable. No nodes had crashed. Pod restarts were minimal. Container memory was healthy. From the outside, it appeared that several independent services had started failing at once. That made the incident confusing. Usually when multiple services break simultaneously, it points to a shared dependency like the database or a network failure. But database latency looked perfectly normal. Network traffic was healthy. One thing looked unusual. Several pods were logging errors. But those logs were buried inside a massive stream of application messages, investigation, and escalation. The first theory was database contention. Engineers ran diagnostic queries against PostgreSQL to check for lock contention. Everything looked clean. Next theory was an object storage outage. The upload service stored files in S3 after processing them locally, but S3 metrics were normal. Meanwhile, error rates continued rising. Support teams reported uploads had stopped. At this point, more engineers joined the channel. One engineer started examining container logs from the file processing service more closely. Buried in the logs was a repeated error message. No space left on device. That was the first real clue. But it raised another question. Which device? Inside Kubernetes containers, that error usually means the underlying persistent volume has run out of storage, but our dashboards showed nothing. We opened the node metrics panel, still nothing obvious. Finally, someone checked the specific persistent volume used by the file service. The disk usage metric read 100%. The persistent EBS volume attached to the file processing service had completely filled up. Root cause. The service stored temporary processing files before uploading to S3. Normally, those files were deleted within seconds after upload. But a recent bug in the retry logic caused temporary files to never be deleted in specific scenarios. For weeks, they accumulated silently. When the disk finally reached capacity, the application could no longer write temporary files. Uploads failed, and the failure cascaded. Once identified, the fix required careful coordination. First, we stopped the file processing deployment to prevent additional writes. Then we mounted the persistent volume into a temporary debug pod. Inside that container, we inspected the file system, mitigation, and recovery. Thousands of leftover temporary files were sitting in the processing directory. We removed the orphaned files manually to free disk space. Within seconds, the volume usage dropped from 100% to under 40%. Next, we restarted the file processing pods. They began accepting uploads again almost immediately. API error rates started dropping as dependent services recovered. Finally, we deployed a patch that ensured files were always deleted, even if retries failed. Total impact was roughly 27 minutes. Post-mortem reflection. What actually failed was a combination of application behavior and missing observability. The real reason it went undetected was monitoring. Disk alerts existed at the node level, but not for individual volumes. Our logging pipeline also masked the errors among normal log lines. The file processing service had been considered low-risk infrastructure even though many APIs depended on it. Engineering lessons. Persistent storage used by containers should always have dedicated monitoring and alerting for individual capacity usage. Application code that writes temporary files must include guaranteed cleanup logic even during error conditions. Cleanup is critical. Observability systems should track storage consumption trends over time rather than only triggering alerts when volumes reach critical thresholds. Sometimes the most damaging outages start with nothing more dramatic than a disk quietly filling up. Vigilance is the only defense.